Welcome to this revision summary on hydraulic models. Just about all the questions that we will be looking at will have two scales in them. They'll be known as distorted scale models, and we use the symbol X to represent the horizontal scale, so that applies to all lengths and widths, and we use Y to represent the vertical scale that will apply to depths. And remember, what we've chosen to define the scale as is the length in the full size structure or system, we call it the prototype, to the corresponding length in the model. And we use P as a subscript to represent the full scale structure or system, and M as a subscript to represent the model structure or system. Now, if we want a model to truly represent the flow that we find in the full-scale structure, it means that every force in the full-scale structure will have to be reproduced in proportion in the model. And you may remember from the class that when we investigated that, we found that it's impossible to do this. All we can do is try and identify the force that has the biggest contribution to the flow pattern and make sure that its relationship to the overall resultant is similar in both the full scale and the model. Most of the models we'll be looking at will have a free surface flow, and in that case we will say that gravitational forces makes the biggest contribution to the resultant acting on an element of the flow. So we will try and keep the proportion of gravity forces to the overall resultant constant in the full scale and the prototype. If we're not entirely clear what we mean by that, what it boils down to is saying that we need to keep the Froude number of the flow at any point in the prototype equal to the Froude number of the flow at the corresponding point in the model. The end result is that we find that the ratio of the velocities is equal to the square root of the scale. And if we have a single scale, it would be the X scale. If we have a distorted scale model, we would write VR equals Y to the half. So in most of the problems we look at, we'll be writing VR equals Y to the half because they will be distorted scale models. So as we said, in most of our problems we'll have two scales, an X scale for lengths and widths, and a Y scale for depths, because we'll be looking at distorted scale free surface models. Why do we have these distorted scale models? Well, of course, it allows us to achieve suitable depths in the model, and also it allows us to get a Manning's roughness in the model, which we can achieve by making the model surface rougher. If we didn't have a distorted scale, we'd probably find that Manning's N was of such a low value that we couldn't actually achieve it in practice. So before we go on and look at an example, it might be useful just to look at a couple of basic results. First of all, as we've mentioned earlier, in the questions we'll be doing, free surface, Froude models, so VR, the ratio of the velocities, will be given as the vertical scale to the half. So that's a very useful starting point we need to remember. Then we could look at the hydraulic radii of the two channels. This is the radius of the prototype, this is the radius of the model. That would be normally defined if we had a wide channel as the depth in the prototype to the depth in the model, or the scale Y. Remember, that's an approximation only for a wide channel, but it's useful to use on occasions. RR, this little subscript R here, is something we use as shorthand for the ratio of whatever quantity we're looking at in the full scale to the corresponding quantity in the model. So RR here is shorthand for RP over RM. The ratio of the longitudinal bed slopes, something that occasionally we might be asked to check, but we don't normally need to work it out unless we're asked. But how would we estimate that? Well, we just consider the longitudinal slope of the full scale channel. For every horizontal distance h, the bed is going to drop by an amount v. So in the model, the horizontal distance would be scaled by x, so it would be h over x, and the vertical distance would be v over y. So consequently we can write for SP v over h, and for SM v over y times x over h. Our end result is that the ratio of the bed slopes, SP to SM, is y over x. Generally, that's what we try to do. We try to express the ratio of quantities or individual quantities as some combination of the scales. So Manning's equation, that's one we're going to use a lot in model questions. We would normally write it as V equals 1 upon n, r to the 2/3, s to the half. Here it is here in its basic standard form. Now, if we took the ratio of Manning's equation in the prototype to Manning's equation in the model, we'd have VR, the ratio of the velocities. We could replace that with the vertical scale to the half. We would have 1 over nr. We haven't found out how to express the ratio of the Manning's roughnesses yet, so leave that to one side. The ratio of the hydraulic radii, well, if we did have a wide channel to a first approximation, we could replace r by the vertical depth, so the ratio of the vertical depth in the prototype to the vertical depth in the model would be y. So again, we need to be careful not to confuse y with any actual depth. Remember, when we're looking at models, y, as for x, is a ratio. It's the scale, the ratio prototype to model. And then finally, the bed slope to the half. Well, we've just worked out that the ratio of bed slopes is y over x. So it would be y to the half over x to the half. So consequently, we can use that version of Manning's to find how to express the ratio of Manning's n in terms of the scale. And there's the result. The ratio of Manning's n is the vertical scale to the 2/3 divided by the horizontal scale to the half. Another very important result. And it would be very helpful if you were able to arrive at that result by the couple of steps previously, rather than just learning it as a formula. And obviously, armed with that result, we're in a position, for example, to calculate the model roughness, as long as we know the roughness of the full scale, by just reorganizing that expression slightly. So that is an essential expression to be able to deduce and use. Well, let's have a look at a typical model question that we might be expected to be able to answer. It's a river model, so that means it's a free surface model, and because it's a river model, it's a model in which we'd have to use distorted scales, i.e. x for all horizontal dimensions and y for vertical dimensions. We're given some basic information, the average flow in the model, the width and the depth corresponding to that, and Manning's n. We're also given a maximum flood flow in the model, and then we're given some information about the space available to build the model. Now, the questions always take the form of recommend suitable scales. And to do that, it's very easy to work out values for x and y, but then we have to justify them. And the key aspect we have to check in order to justify our choice of scales is the Reynolds number of the model flow. And we would need to calculate that Reynolds number at the minimum flow that we're going to model. And the reason we do that is because by building a model, the Reynolds number will be distorted in the model. It will not be the same as the prototype, and we need to just satisfy ourselves that the flow in the model will continue to be fully turbulent, so we need the Reynolds number to be above 4,000 or so. Calculating the Reynolds number is the only thing we should be expected to do without being asked. Any of the other model properties we will be asked to do. So, for example, comment on the surface roughness. That basically means calculate the model surface roughness and then say something about how it could be achieved. Estimate the maximum discharge that the pump in the laboratory will be required to deliver. That's just saying find the maximum flow in the model. That would be corresponding to the maximum flow in the prototype. And Anything else, such as find the model bed slope or comment on the model bed slope, if we were expected to work that out, we would be asked for it at this point here. If we're not asked, we don't need to do it. So as we said, working out the horizontal scale, very simple. We look at the length of the full scale that we're looking at, 7.1 kilometers, 7,100 meters, divide it by the space available, we get 394.4. Now we don't want to use a sort of awkward scale like this, so we need to round it up in this case. Remember, if we look at our definition of scale, a slightly bigger number for the scale represents a geometrically smaller scale. So we'll go up to say 400, just round it off. What about the vertical scale? Well, here there's a minor subdivision between the way the questions are framed. In this particular question, we have not been given the model flow. In fact, we've been asked to find it. So the way we choose a vertical scale is just on the basis of a rule of thumb. So we go for a scale 5 times bigger than the horizontal scale. That would be a number that is smaller, so we divide 400 by 5 and get 80. We'll have a look later and just see that if we were given the model flow, then we can actually calculate y from that information and probably get a better or a more optimal value of y on account of that. But in this case, we weren't given the model flow, we were asked to find it, so we'll have to find y just on the basis of our rule of thumb. Okay, well, this is just for illustration. If this was an exam question, as I've already said, we haven't been asked to find the model slope, so we wouldn't need to do it. But let's just assume that we had been. How would we do it? Well, you know, we worked out earlier that the ratio of the longitudinal slopes, SP to SM, was given by y to x, y the vertical scale, x the horizontal scale. So if we wanted to find SM, we would need to know the slope of the full-scale model. And if we looked at our question, we'll see that we haven't been given that. So we'll have to work it out. The only way we could work it out is to use Manning's equation with SP as the unknown and taking the flows that we are given and the width and the depth that we're given for the minimum flows. Now we could, although we don't know whether it is a wide channel, but we could get that estimate a lot more easily if we assume that we've got a wide channel. So Manning's for wide channel, expressed in terms of the flow per meter width, little q, subscript p means prototype, little q equals the 1 upon n p, that's n in the full scale, the depth to the 5/3 times the slope to the half. Deliberately avoiding the use of y here, the depth in the prototype would be approximately equal to r if it were a wide channel. So d to the 5/3 s to the half over n, from which we work out n here, 0.00043. And to express a slope, of course, we normally express it instead of, well, we can express it either as 0.0043 or 1 in 1 over 0.00043. This is the more normal way to express a slope in engineering terms. So 1 in 2,326. So we've chosen our two scales y and x. We've calculated SP from Manning's equation, assuming a wide channel. So hence we can calculate SM, the model slope, which is 0.00217 or 1 in 460. And if we think of a 1 meter length of the model, that's 1,000 millimeters, then 1 in 460 is very roughly, it's almost 1 in 500, so that very roughly 2 millimeters per meter length, which you could just about achieve physically in a model. Now this part is the most important part really, because as I've said at the beginning, the one thing that you will always have to check in a model question is the Reynolds number of the model, even if you're not specifically asked. We need to look at the flows given. If we are given a minimum and a maximum flow, then the Reynolds number should be chosen for the minimum, because we're worried about it falling below the point where the model flow would be turbulent. So if we're going to check the Reynolds number of the model, we should remember that the Reynolds number of the model is the velocity in the model times the hydraulic radius of the model times the density of the fluid in the model over the viscosity of the fluid in the model. These, of course, are for water and are given. So the first thing we're working out here is the hydraulic radius of the model. Now, I know earlier we said we could assume the model was a wide channel and we could calculate or estimate the hydraulic radius as just being given by the model depth. But when we're checking the Reynolds number, if it's at all possible, if we're given enough information, we should try and work out the hydraulic mean radius of the model from the full expression for hydraulic mean radius, which of course is A over P. So the hydraulic radius is A over P. And the area of the model is the breadth of the model times its depth, and its wetted perimeter is its breadth plus twice its depth. Now we were given the full scale width and the full scale depth at the minimum flow. So to find the model width or breadth, we just divide that by the x scale because it's a horizontal dimension, and to find the model depth corresponding to 4 meters depth in the full scale, we divide by the y scale. And hence we can calculate the, if you like, true value of hydraulic mean radius of the model, 0.0278. The only other thing we now need to check is the velocity of the flow in the model corresponding to that minimum flow in the full scale. So the velocity in the full scale would be the flow in the full scale divided by the area in the full scale, which is the flow divided by the breadth times the depth. So that's 300 over 50 times 4, 1.5. Now we make use of that standard relation that the ratio of velocities is the vertical scale to the half, and that allows us to calculate the model velocity, which is 0.168. There we have it, 1.5 over the square root of the vertical scale, here, y to the half. So now we can calculate the Reynolds number of the model. Here it is here, Vm, Rm, rho m over mu m, as we wrote up here, and when we substitute in for the velocity of the model, the hydraulic radius of the model, and for the density and the viscosity, we get 4096. In reality, we wouldn't accept that value of Reynolds number. We would go back and readjust our model scales. We would want it to be well away from this point here. But for the purposes of the present question, we will just leave it as it is. Okay, now we're going to check the model roughness because we've been specifically asked to do so. We start with Manning's equation, V equals 1 upon nr to the 2/3 s to the half. That's the basic form of Manning's equation for a channel, whether it's wide or non-wide, before we make any simplifications. And if we write that for the prototype and for the model and take the ratio, that's the little subscript r's here, we get the result which we did get earlier, that the ratio of the roughnesses, np to nm, written in shorthand as nr, is rr to the 2/3 x to the half. And if we had assumed a wide channel, then we could just use the vertical scale here, y to the 2/3 x to the half. But in these problems, if it's feasible to calculate the ratio of the hydraulic radii as it is in reality, it's better to do so than to use a wide channel approximation, unless of course we've been told that the channel can be assumed as wide, which we weren't in this case. So that means we want to calculate the hydraulic radius of the full scale. It's fairly easy to do because we're given the various information at the minimum flow, 3.448, and we'd already calculated the hydraulic radius of the model, so the ratio of the hydraulic radius of the full scale to that of the model we can work out easily, 124. So in this case we can work out that on a sounder basis than just a wide channel assumption. but if we're pushed as an approximation, we could just use the vertical scale here. So NR is R to the 2/3 x to the half, work it out, 1.224. So the roughness of the model is the roughness of the prototype over NR, 0.028. Now, normally Manning's roughness in channels ranges from 0.012, 0.014, 0.016, typical values. So 0.028 is a very high roughness, particularly for a model. So the comment we usually make is that that model will have to be artificially roughened. And as it turns out, it's quite a useful thing because it means that we can calibrate the model against known flows by adjusting the roughnesses. Just as a matter of interest, if we had gone for the wide channel approximation for NR, y to the 2/3 over x to the half, then the result we'd have got for NM would have been 0.038, which is quite a bit higher than the 0.028. So there is a bit of a difference, and that's why, if we've got the information available, preferable not to make the wide channel assumption here, but to work out R as we've done above. Finally, the maximum model flow, i.e. the maximum flow the laboratory pump would have to deliver, that will be based on the higher of the two flows given for the full scale, i.e. the 850 cubic meters per second. And here's another important result that we should be able to deduce. Remember that Q equals A times V in any channel, so the ratio of the flows, QR, would be the ratio of the areas times the ratio of the velocities. Now the ratio of the velocities we know is y to the half from a Froude model, and the ratio of the areas is x times y. We can work that out. So QR is xy times y to the half, or xy to the 1.5. And that's a result that we're going to inevitably use if we ever have to work out the model flow. So QM would be QP over xy to the 3/2, work it out, just under 3 litres per second. Down below here we've just given a brief resume, which is something you should be able to do just to show that the ratio of the areas, prototype to model, are in fact given by the product of the two scales, x, y. You can see how we've done it. In the full scale, the area of the prototype is b times d if we had a channel of breadth b and depth d. And in the model, that breadth would be b over x, the depth would be d over y, so the area would be b over x times d over y. So the ratio of the two areas would be given by x, y. So again, we should be able to work that out for ourselves, preferable to just remembering it as a standard result. Now here's another example which we're not going to work through in detail here, but we're just reminding ourselves that, as we said earlier, there are two minor variations in problems as to how we can calculate the vertical scale y. In the previous problem, we did not have any information about the maximum pump capacity or the maximum model flow. In fact, it was something we had to find. So we just calculated the vertical scale by a rule of thumb, making it 5 times the horizontal scale x. But if we're actually given this maximum pumping capacity or the maximum model flow, then we can actually use that to calculate, if you like, a more optimal value of the vertical scale. In fact, the way we do it is we make use of the relation that we just talked about at the end of the previous problem, that the ratio of the flows, prototype to model, QR, is xy to the 3/2. And if we're given QP and QM so that we can calculate QR, and we've chosen x on the usual basis of the length of the prototype to the space in the model, then of course the only unknown thing is y, so we can deduce or calculate a y from that data. So QR xy to the 3/2, so y would be the ratio of the flows, QR, prototype to model, over the scale, horizontal scale x, all to the 2/3. and in this model, this problem, of course, it comes out to be just under 10, so we'll round it up to 10. Otherwise, the rest of this problem would be dealt with in the same way as the previous problem. So that concludes our brief revision of models.